The way that post-order traversal works is we visit a node, but we're always trying to follow a left branch. So we look to explore all the left branches. When we've got no more left branches left, we backtrack to the node. And then we try and go right. As soon as we encounter a new node, we try and go left. Okay? So we try and go as left as possible. So this should be your clue that the thing on the very leftmost part of the graph at the bottom should be your first item. Okay? Once you've exhausted for a particular node all the potential left branches and right branches, that's when you output the node. That's why it's called post-order traversal. So it's after you've done everything you can possibly do from that node. So if I was to do this raw without using a graph, I'd start at the root, because we always start at the root, which is 50. And I go, oh, there's a left branch, let me follow it. So I'm now having to keep in my head where I was. Okay? Which is what the algorithm does for you. Right, I'm at 45. Oh, we've got a left branch, let's follow it. Oh, I'm at 20. There's a left branch, let's follow it. Oh, I'm at 5. Oh, no left branch. Let's try and follow the right branch. Oh, there's no right branch. Okay, put the pen on it now. Right, okay, so I've found my first node, because I've explored all the branches. Right, I've now got to backtrack, so I've got to go back up. So you can do it if you use your finger as a stack, effectively. So I'm like putting my finger on 20, and I'm going, right, I've gone all the left branches, now I've got to try and follow the right branches. So I follow my tree down, and I get to 31. I go, all right, try and go left. Oh, I can't. Try and go right. Oh, no, I can't. Right, okay, output the node then. Mark it as visited at that point. Then I backtrack again, and I can see I've got back up to 20, but I've just come from a right branch. So I've explored the right extent of the tree, so I can write 20 down. Then I backtrack again, and I look at 45 and I go, oh, there's a right branch, let's follow the right branch. Get to 48, well, hey, let's go on the left branch hunt again. There aren't any, luckily, otherwise I'd get really annoyed. I try and go right, I can't. So I go, right, okay, I've done everything I can do at 48, so let's output it. Then we backtrack. Backtracking is a key word. That's what this is, a backtracking algorithm. Okay, so I backtrack, get back to 45. I've just explored the entire right branch from 45, so I can output. Then backtrack again, get to 50. Don't output 50. We've got to explore the right-hand side of the tree now. Okay, so we now go right. We get to 76. And we say, oh, 76 got a left branch, let's go left. Let's always try and go left. So we get to 60. Luckily, it's a leaf node. So we go, oh, no left, no right. Output it. Then we backtrack and we go, oh, there's a right branch from 76. Let's go right. So we go down the tree, we get to 98. Oh, let's follow the left branch. Left, then right. So we go left. We get to 88 and we go, oh, no left, but there is a right. So let's go right. Okay, and so you can, if these trees get big, you lose this. You'll lose your mind completely. So I get to 92. Luckily, it's a leaf node, so there's no branches to examine. So I do everything I can. I output 92. Then I backtrack, get back to 88. I've explored the right-hand side of 88, so I can output it. Backtrack. I've got 98. There is no right branch, so I've explored all the tree below 98, so I can output it. Then backtrack again, get to 76. I've just explored the right-hand side of 76, so I can write that out. Backtrack again, get right back to the root. There are no more branches to explore. So I can do it like that. Okay? The way they tend to mark these is they like group mark. So they'll say, oh, you got these 3 correct, you got the next 3 correct, you got the next 2, you got a final, the whole thing was correct. Okay? If they ask for an explanation, then you're going to talk about post-order traversal follows the left branches as far as they can go, then it will explore the right branches. Once both left and right branches have explored, then we output the node. That's what you need to say. Right, so that's the, oh my god, I'm crazy, I really want to screw it up in the exam method. The better method is to do the cutting of the nodes. So post-order, so we want to make a line from the center of the node after the node. So we're going to make a little mark like that on every node that goes to the right, post. So I'm going to just prep my diagram up. Just make sure you don't miss a node out. It's not the world's most amazingly drawn tree, is it? To be honest. They couldn't even be consistent with the arrows. Right, so we do that, and then we draw a line anti-clockwise, starting from the top of the node. And we write down any node that we cut, our little outline. We've got to try and stay close to the tree. That's the key bit. So I'm just going to go round and round, and I cut. So I write down my 5. Keep going round. So this is doing the same process. This graphical way of doing it is doing the explore the left, explore the right. Okay? Don't do anything with the node until you've visited both parts. It's just doing it graphically. So we go round and round and round. That's 20. You should see, unless I've totally messed it up, I should get the same list of numbers. 45. Right, so here's an annoying bit of the tree. We go around, make sure you don't miss that out. So 60, go around. 92, matching so far. 88, 98, and then we just fly back up, 76. You always know when you do a traversal, not a search, when you do a traversal, the route will be the last thing you write down. Okay? The only one they ask us to do is this post order one. Alright, so if you do a traversal of a tree, it will be the root node that ends up last. But you can see that it favours the left hand side, and that's the way that it works, because it's left, right node. Okay? Right, anyone got any queries about that one? Right, okay, let's get on to the meat dwellers. Right, Dijkstra. Oh, go on, Ralph. It's not, no, it's not sorting it, but it's flagging it for processing. It's forcing the processing order, that's all. It put you, yeah, it's post order. You could say it's post order, yeah. It depends what the tree's being used for, Ralph, so you have to be careful, really. What, down like that? Yeah. That's if you wanted to make a list in order. They don't ask you to do, I don't know why. Why they can't give you an ordered tree and say, like, produce it in, like, alphabetical order or numerical order, I don't know. If you do the line down the middle, you will get them in that order. Because you can see you'll get 5, then 20, then you'll get 31. So you'll always visit them correctly. Yeah, it's weird. It's weird. They took the context away. It's to do with syntax trees and compilation. I don't know why they've got rid of all that. It's quite interesting stuff. Right, okay, so Dijkstra. Remember, it's about clearly showing the process you've gone through. All right? If you want to, you can explain and you can write stuff to explain what you're doing. But unfortunately, that's going to take time, isn't it? So we want to try and minimise and maximise the amount of points we get for a particular amount of time we spend on the question. The exam paper is 2.5 hours long, which sounds like ages, but once you get into like some of the more meaty problems, like creating algorithms from scratch, that can actually suck up so much time. If you're writing essays, the 9-mark questions, they suck up so much time. So anywhere where we can bank a little bit of time, that's good for us. So we're going to try and make the following of it clear. It's Dijkstra. Okay, so we've just got to maintain a list of nodes, parents, and one cost. Alright? It's Dijkstra. So everything is available to search to start with. So we just write down, and I'm just going to do it alphabetical so I don't miss one. I can see it's alphabetical on here. So I'm just going to put A, B, what have we got? C, D. Do not be surprised if they miss out letters and things. And F. So there's 6 nodes on here. So we want a parent, so I'm just going to put par, and then we've got a cost. Right, we're starting at A. So the cost for A is going to be 0. Remember, that's the travel cost. How far have we travelled so far? I haven't gone anywhere, so it's 0. Everything else is infinity. Okay? If you don't like drawing infinity symbols, just put INF or something like that. The key thing is that you do not scribble out previous numbers and values. Right, so the process, simple. Each time, if something's in the open set, look for the smallest cost so far. Pick it. Mark it as closed. Look at the neighbours. How much is it going to cost to get to those neighbours? Update if we need to, where we found a better, cheaper cost. Keep going until you locate, you select the node you want to end on. So we're going to keep this process going until we pick F. Okay? Right, so I'm going to look at this. I've got 0 for A, so that's going to get picked. So I'm going to mark it as closed. I'm going to put a 1 next to it so the exam board know that I picked it first. Okay? I'm going to look at its neighbours. We've actually got an undirected graph here. There's no arrows, so everything is fair game as terms of a neighbour. Right, so I'm just going to go for B. So it cost me a further 5 to get to B. It's cost me nothing so far to get to A. So I'm going to update from infinite. So all of the, you've gone wrong if none of these get updated. So that's going to now have a cost of 5. It's going to cost me 5 to get to B. And that is from the parent A. Okay, I've got another neighbour, C. Right, so it's going to cost me a further 3 to get to C. It's currently, because I'm at A, and I can see that because I've put this marker, and I can see which node I'm currently on. All right, because it's the highest number, 1. Right, it's going to cost me 0 plus 3. So that has been superseded. Cost of 3. And that was from parent A. I've got another neighbour, D. Right, so it's currently infinite, so that's going to be bettered. It's going to cost me 3 to get to D. And that's from parent A. There are no more neighbours. Okay, so I've done one loop of Dijkstra. I'm just going to do that again now. So I'm going to look for the cheapest cost. Right, we've got a choice. They will, if they're writing these questions properly, always have you make these choices. Right, so it doesn't matter. We're going to pick the one that's the first. We're going to pick C. Anyone pick D when they did it? No, it doesn't matter. Right, so I'm going to pick C. So I close it straight away. And I say, right, this is the second one I've picked. And I'm going to look at my neighbours. I initially, because I'm just looking at the diagram, look at A and I go, right, oh, but I say, no, hang on, A is closed. Can't look at A. So ignore that. All right? If you don't close something, you will end up going in a loop, infinite loop. So you must make sure you remember to close things. So A is off the table. I've got 2 neighbours then. I've got E. E's currently infinite, so it's going to be bettered, the cost. Right. It cost me a further 3 to get to E, but it's already cost me 3 to get to C. So to get from C to E is going to be 3 plus the extra 3. So that's going to be 6. Okay, so E is going to cost me 6, but that was from parent C. Right, so the other one I've got is this F thing. That's where I'm looking to get to, but I'm only looking at it as a neighbour. I haven't visited it yet. So please don't say, oh, I've finished, because you haven't. Right, so it's going to cost me, and these were nice numbers on this one. The next one. Right, I'll need some help when we get onto that one. Right, so it's going to cost me a further 3 to get to F. It's already cost me 3, so that's again going to make F cost 6. And that's going from parent C. So we've actually got a cost value for every node so far, but we haven't finished. We haven't reached our goal. So let's go around the Dijkstra loop again. Pick the cheapest. So this time D is going to get picked because it's the cheapest, 3. So I'm going to close it, mark it as the third one I picked. I think I've never asked students to do that before, but I think that's actually quite important because it shows the order that you visited. And they do tend to, the mark schemes are overcomplicated for these. And they do like saying, oh, you then visited this. And you're not having to write a statement saying, now I picked D, which you don't want to do. Nobody wants to do that. Right, so I've picked D. I need to look at my neighbours. So initially I look at A, but I can see it's closed, so I can't pick it. E's still open though, so let's have a look. So it costs me from D 2 to get to E. I've currently got a cost of 3 to get to D. So my total cost to go from D to E will be 5, which is better than what's currently there. So I'm going to mark that as bettered, and I'm going to put 5 as my cost. Now that means the parent is updated because I've got a better cost coming from D. Now I've been stupid here and I've put my parents too close to my markings for my clothes, but I think I'll get away with it. Okay, so I've updated that one. So we can see that if I wanted to travel to E, I wouldn't go via C. That's what we can conclude from that. In case they ever ask what other judgments you can make from your data. Right, okay, so E's got no more neighbours. Well, it has, it's got C, but that's closed. So we've finished. Okay, so we're going to go around the Dijkstra loop again, and we're going to pick the cheapest. So we've actually got B and E that are 5. And again, I'm just going to pick the first one. So I'm going to pick B. Okay, so I'm going to look at its neighbours. It's got a neighbour A, that's closed, so I can't do anything. And it's got a neighbour F. F's open, so let's see if this is cheaper. So it's cost me 5 to get to B and a further 2 to get to F. That's not better than 6. So there is no change. So actually that's it. We didn't update anything in that loop. If you wanted to, you could put something there saying when you pick that, saying cost not better to F. You could put something if you really, really wanted to. But I don't think it's necessary. Okay? Unless you feel like you've got 5 minutes at the end of the test and you want to go back and you just want to annotate a little bit. It's up to you. Right, okay, so I've closed that one off. I'm going to go back around my loop. My cheapest is now E. Okay, so I'm going to pick that, and that is my 5th pick. Right, so I'm going to look at my neighbours. So I'm at E. I've got a neighbour D, but that's close, so there's nothing. I've got a neighbour C. Well, there's literally nothing to update. And you can sort of see that because E's off in the middle between two nodes that we previously looked at. So nothing to update there. So that leaves us with one final node to pick, F. We don't do anything else because it's where we're going. So we stop at the goal. Now, the majority of the marks then are for showing that process of picking and the updating of E. But we want to get that final mark for the route because we're not going to forget to put the route down because we're not stupid. So we put F down and we say, right, okay, and I tend to always do it like this. Put the where did I come from and then I'll have a look. So I look at that and I say, well, I came from C because that's what the parent says. And I say, well, where did C come from though? So I look for C and I can see C came from A. I then look at A and I see that it's got no parent, so that must have been my start point. So that's my double check. And that's my route. Anyone got any queries about that? Dijkstra is actually super simple. You haven't got loads of columns to worry about. Okay, right, final one then. Oops, he says scribbling all over his diagram. Right, okay, A star. You can, like I said, you will spot A star because you've got loads of numbers. This is a hideous bunch of numbers. Why they came up with these numbers, I have no idea. But they did. And unfortunately, that's what we go with. Just as a point of interest, you can see that even if I wasn't reading this question properly and I didn't realise that E was the goal, I can guess E was the goal because the heuristic, remember, says how far do you think we've got to go to get to the goal? Well, if it's 0, then that must be the goal. Okay? Right. I'm not too worried about the previous questions, but the previous questions were... let me load that. I'll do that one. Right, so the question started off said, what is the data structure? What are you going to go with? What data structure is it in that diagram? Yeah, it's a graph. It's a what? A graph. It's a graph. 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 You're too posh. You're too posh. It's graph. G-R-A-F. It's just spelt funny. Right. What might those heuristics represent in that image? I mean, the context is airports. So there are two things that it could be. What's an obvious thing? Yeah, some relationship to physical distance. It might be like tens of kilometres or hundreds of kilometres, I don't know. What else could it be though? Think about airlines, one of the things that they worry about. Fuel costs, could be, couldn't it? You know, that would be one. Oh, it's going to cost us 90 units of fuel to go from N to E. It could be. All right, so there's always different things that it could be, the heuristic. And then the purpose of the heuristic is what? No, it doesn't do that. That's the outcome of it. It's to make you favour nodes that are potentially closer to the goal. That's what it is. So you're going to disregard nodes that have got high heuristic values. So actually, the reason it makes it quicker, Ralph, is because you are effectively saying, I'm going to ignore some of the nodes in the graph. Now, obviously, with something a little like this, there ain't much ignoring going on. But with a huge graph, yeah, the more data you don't have to look at, the quicker something's going to be. It's a bit like binary search, isn't it? The fact that binary search is quicker is because you throw data away. You say, like, I'm only looking at half of it each time, and I'm going to only look at half of it again. So it's that sort of process, and that the best algorithms will always do things where they can disregard bits of data. Right, okay, so we've got to go from H to E. So this is a little bit more complicated because we not only have our nodes, so let's draw our node in. And again, just like in Dijkstra, I'm just going to make a list of all the nodes. There's no sensible alphabetical sequence here, so we have to be careful. So I'm probably just going to start at H, and I'm just going to, in fact, I'm just going to put H down. All right. Whereas Dijkstra needed to populate the open set, in A star we can do, but we don't have to populate it to start with. I'm just going to put H in there. Now, I've got loads of costs. I'm going to put my parent over here again, on the left-hand side, mainly because when I do the root back, it's easier to see the parent and the node. I'm not like looking across a horrible line of scruffy writing that I'm going to do. Right. So I have got 3 cost values. Always write them in this order. G first, but remember to leave a gap. Okay, because these things might update. The heuristic will never change in this static thing. So you don't need to leave much of a gap, but I'm going to leave a little bit of a gap. And always do that. Put a plus. So that you're indicating to yourself that's the maths you're doing. And then put equals and then F. So it is only G and F that will update. We can, the reason why sometimes I might put all the nodes down is so I can write all the heuristics down. So I don't cock it out. But it doesn't matter. Right, so my costing, my G cost is like the Dijkstra one. It's the distance we travelled so far. So I'm going to put, for my start node, I'm going to put 0. I'm going to put my heuristic in. And because I've written this little plus thing, I'm going to say, oh yeah, I've got to add those two together. So I've filled in my full cost. So that is the setup. That's where we start. Parent, I'm just going to put a null marker, just a dash, to mean that's where I started. Right, the loop. Similar to Dijkstra, we look for the cheapest that is available, that is in the open set. Well, this is quick to start with because there's only one item in there, so it wasn't much of a search. Okay, and it's this that I look at. So this is what we look for, lowest of this. If we get 2 identical Fs, this is our second lowest. Check. If needed, but only if they've drawn the graph really well. Okay. Right, so I'm picking H. So just like Dijkstra, then look at my neighbours. So I've got a neighbour N, so I'm going to write N in my open set now. But I've marked H as selected. Gone. It's no longer possible to manipulate the values of H. I've got N though. So I say, right, well, I've travelled 0 so far. It's going to cost me a further 210, and here's where the nightmare starts. No calculators, remember. So if you're like a bonehead at mental arithmetic like I am, then you're in for like a rocky road. Loads of long working out. I don't know why we're not allowed a calculator, it's so stupid. Right, so I've got to add, luckily, 0 to 210. So I'm going to say, well, the cost for travelling to N is going to be 210. Okay, so that's nice. I can add that one up. Now, the heuristic for N is 90, so I'm making sure I write that down carefully. Now I can do the arithmetic. So this is where it all starts getting horrible. Luckily I can do that one, 300. Double check me because I will screw this up. Okay, so I've calculated what potentially is the full cost by going via N. That's what I've got. So that was H as my parent. Now what you could do, when you visit and you add a node for the first time, you could whack the parent straight in. Okay? I tend to like do it this way, so I'm looking at calculations, then I put the parent in case I'm doing an update. And then I'm just doing the same process. Right, so my other neighbour is G, so let's put G down as a node, just to confuse us with G. There's the cost. If you want to put GC, HC, FC to stop that happening, then please do. Right, okay, so to get to G is going to be 0, the distance I've travelled so far, plus 25. Now, can you see how this does not? This is very abstract. There's no relation to the actual physical position on the page. So my costing is 25. My heuristic for G is 70. Right, now I add them two together, so here we start getting trouble. 95, am I correct? Yeah. Right, so that was from parent H. There are no more neighbours, so we've finished one loop of A star. So all we've got to do is we've got to just do that process again. So we've got 2 items in the open set. So again, one of the benefits you're getting with A star is that the open set doesn't contain the entire graph. With Dijkstra it did. Okay, so you have to do more intelligent things with your open sets to speed up. Right, so I've got 2 things. I'm not looking at the G column, I'm looking at the F column for my cost. Alright, so I'm going to pick the one with the cheapest cost. So the one that looks like it's going to be the cheapest, and that is G, because it's 95. So I'm going to pick that one. Right, and I'm going to look at my neighbours. So I'm looking at G on my graph. H is a neighbour, but it's closed. Do not touch it. I've got a neighbour called L, so let's add L to my table. It has got a cost of 51. Where did it get 51 from? I don't know. 51. Right. I can't work that out yet because I need to know how far have I travelled so far. So to get to G cost me 25. It's going to cost me a further 51 to get to L. So now I've got to add 25 and 51, which I think is 76. Okay, right. My heuristic for L is 50, so that's a nice number. But I've now got to add these two together, so that's 126. Have I got that right? Yeah. I will screw this up, so don't just let me blindly go along on this. Right, so that was travelling from G. It's the first time we added it to the open set, so it was always going to have G as its parent. Right, the other one is one with a minging number on it. Not as minging as that one, but a minging number is M. So I'm going to add M to the open set. Right, so it's cost me 25 to get to G. It's now costing me a further 176 to get to M. So 25 plus 176, is that 201? Right, so that's cost me 201 if I choose to travel G to M. My heuristic is only 20, so M's pretty close. So that gives me a final or full cost of 221. That was travelling from G. No more neighbours. So we're just going to go around the loop. So I've only looked at or visited 2 nodes so far. So now I'm looking on the F column for the next one. So I'm actually, for my sanity's sake, I'm going to put an X, because I'm looking quite far across now. I'm going to put an X on those 2, so I know not to pick those. Okay, just, you know, anything like that, however you make it, so it makes it easier for you to not mess it up. Right, so I've got 300, 126 and 221. I'm going to go for the lovely 126 and pick that one. Okay, so I've picked L. I'll need to look at the neighbours. It's only got 2 neighbours. G is in the closed set. It's gone. I don't have to mess with that. But I've got E, which has got a lovely number associated with it. God. Right, so to get to E, so I'm going to add E on here. To get to E from L, it cost me 76 to get to L. It's going to cost me another 307, which is a horrible number. So that must be a total cost of 76 plus 307, which is probably 386. Is that right? So 386. The numbers escalate in violence. They really do. Right. The heuristic for that is 0. Oh, have I got it wrong? Well, what should it be? L cost me 76. 383. See, easy. Awful. It's because of all those 25s. It's all them 25s that they had. It screwed me up. What was it? It's 383. Yeah. But the heuristic is 0. So that one's easy to do. I can do that one. Right. Okay. My no more neighbours. So I'm done. So I'm just going to mark that one because I've marked L off. Right. I've got to go again. So I'm looking at my choices, and they're not nice choices. 300, 221 or 383. I'm going to go for 221 because it's the smallest. So I'll pick M. 4th pick. Oh, what did I miss? What did I forget to do? I didn't put my parent L. Okay. Because I messed up, I got myself out of sync there. So be careful with that. Right. Okay. So I picked M. Neighbours of M. N. Oh, N is open still. So we need to have a look at this, see if it's updatable. Right. Okay. To get to M was 201. To get to N is a further 233. Luckily, to get to N currently is 210. So I'm not even going to bother trying to add it up. It's way bigger. So it's like, woo, thank you. I don't have to do that one. Ooh. But we have got E. E's open as well. So let's have a look at this. This is an important one because E's the goal. Right, so to get to M cost me 201. It's going to cost me another 185. I can't do that. I just really can't do that. It's going to cost me 185. It's going to have a 6 on it, yeah. 386. Right. It's currently 383. 386 isn't better, is it? So we have not bettered our route. Okay, so we do not update. Everyone happy with that? No more neighbours. So let's just put a little marker there and say we've done that one now. Okay. The pain continues because we're still not going to pick our goal. So we go 300 is cheaper than 383. So let's pick N, number 5. Let's have a look at the neighbours of N. Luckily, H is closed and M is closed, so there's nothing to update. So we're done. Right, final route round the loop. We pick E. It is our goal, so we stop. But we've now got to draw out the route. So let's just look. I don't need to look at the graph. I'm looking at my data. So I'm going to write E down. Where did E come from? E came from L. Where did L come from? L came from G. Where did G come from? G came from H. Where did H come from? No one. It was the start. So my answer is that. Okay, so for this one, we haven't got any updates to the data. The key is the order that we visited the nodes. You can always work out. So if they said, what order did you visit the nodes? So we can say we visited the nodes H, G, L, M, and that was the 6. N, and then E. That was the order that we visited nodes if we need to do it. Okay? So here, when we're going through this process, if we don't do any updates, it might be that what you want to do is say what you rejected updating. I don't know. That starts making it messy and complicated. Okay? So when I picked N and I went, no, N no better. I have to work them out anyway, but how can I show that without clumsying up the diagram? That's my key problem. Something that you need to think about. What might be a good strategy for doing that? Okay? Anyone got any issues with that? So the hardest thing when you're doing that is this bit. Is remembering that it's F that we look for the lowest value. If we get two that are the same, which they didn't manage to do, okay, look in the H column. Because we go for that, and if you can't remember why, just think, well, the H column's telling me which is the best, what the guess is left. So the one that's the same, that's got the lowest potential guess, that's got to be the one to pick. Okay? It's not agnostic, remember. We know something, that's what the H gives us. But always do this bit. G plus H equals F. And then you will not mess that bit up. Okay? So, yeah, it is slightly more complicated than Dijkstra, but actually the process is identical. What you find is you can simulate Dijkstra's algorithm by creating a heuristic value for all the nodes of 0. Because Dijkstra is a subset of A star, not the other way. Even though Dijkstra came first, but you find that with things when you've got algorithms and problems. Okay, right, I'll stop the vid there.